Hi everyone. So in this lecture we will talk about growth and decay of current in LR circuits. Okay. Now we have already studied CR circuits, but here we will talk about LR circuits. Now I hope you can see this circuit on the page here. Now at time t is equal to 0, suppose S1 is closed. Now when it is closed, when it just started, so I would say when S1 is closed, t is equal to 0 and I is equal to 0. So if there was no inductor, suppose there would have been no inductor, let's say in one scenario there is no inductor at all. So what would happen is instantly the current would have reached the maximum value. So let me let me write it. If there was no inductor, if there would have been no inductor, then I would have reached maximum value instantly. Okay, so in that scenario we could have said that I max is equal to I naught E by R. Okay, but that is not the situation. Now, okay, now before going forward, let me reiterate what is the role of inductor. So what does inductor do? Inductor opposes current and thus it takes time for the current to grow. Basically, inductor, let me write this, inductor always opposes current. Initially, and thus it takes time for current to grow. Okay, now remember one more thing. Suppose it reaches steady state. Now steady state is, see, the initial state which we are talking is this. Okay, now if let me write it by a different pen, if t is infinity means steady state, when there is a steady state, at that point I is equal to I naught and it current becomes constant. Right, now the point here you have to remember and keep it in mind that this plays role, let me write it here, plays the role when current is changing. So see, this inductor, let's say at t is equal to 0 the current is I is equal to 0, and after some time the current become constant. Now that is called that is a saturated state, okay. Now, or rather the right word is steady state. Now, so let me write that as well, steady state. Now, between t is equal to 0, when the current is I is equal to 0, and till steady state, inductor plays the role. That is why I have written this inductor plays the role when current is changing only. Okay, now when the current is at steady state, constant, then it plays no role. That is number one, you have to note, which I have written it. Number two, Inductor is something like this. It will always oppose the change, and we already discussed this. Let me tell you again. For example, if the current is growing, what will inductor do? It will generate a current which will be in opposite direction, so it will not let it grow. If the current is dying, then it will generate the current in the same direction so that it will stop it and not let it die. Okay, so this is basically the role of inductor. Now let me reiterate again. In this circuit, inductor plays the role only when there is a change, or whenever there is from t is equal to 0 to t is equal to infinity, or steady state. So basically infinity doesn't mean very high after too much of time. No, t is equal to infinity means when the current becomes constant, or current becomes constant. Okay, so from here to here, inductor plays the role. Okay, so now guys, let's go a bit more in detail. Now let's assume at some time, let's say t is equal to t dash, and we should know where t is less than infinity and less and greater than 0. Okay, and I is equal to I naught. Okay, now, and we should know this also, that I naught is between, or I is between, 0 and I naught. Okay, now look at the circuit. We are right now talking about only from t is equal to 0 to t is equal to infinity, or the steady state. Okay, because after the steady state is achieved, then there is no role of induction. Okay, so we are just thinking about something in the middle. Now in this case, if we just apply Kirchhoff's law, applying Kirchhoff's law, if we apply Kirchhoff's law, look at this circuit. See, E, okay. Now this is coming this way and it will go here. So what will happen? An induced current will, see, this current is increasing. Because this current is increasing, this inductor will produce a current which is opposite to this, to decrease this current. Now if that is the case, then what would be the EMF of that? We can say this, or let me draw by pen. So it will be something like this. Okay, got it? Because if this is the induced current, then the current should flow from positive to negative. So whichever is the arrow, whichever side the arrow is, should have a positive and the other should be negative. Okay, very good. Now if I apply the Kirchhoff's law says that if the current is, here the current is flowing from positive to negative. So Kirchhoff's law says if the current is from, let's assume the direction of the current is this, as denoted by this. So I have just drawn this. Now if you look at this, you will see the current is from the minus to positive in the battery. So Kirchhoff's law says that if the current is from negative to positive, it should be considered as positive. So it is plus E. Okay. Now coming here if you see positive is here, negative is here. I already explained why, because the induced current is this way. So it will be minus. Now what we have studied in the previous chapter is L, the EMF value would be di by dt, correct? Now going forward, the current would be in this direction, correct? So current, so as per Kirchhoff's law, it will be minus IR, okay, and then again it goes back. So it is a closed loop. So net EMF would be 0, okay, or I can say E minus IR is equal to L di by dt. Okay. Now further I can say dt by L is equal to di by E minus IR. Okay. Simple mathematics. I just manipulated it a bit. Okay, right. Now let's integrate it. So this is what I have just put it in a different way, and then I am integrating both sides. Now if I integrate and let's, on the left hand side, let's integrate from 0 to t. Okay, on the right side it is current, so 0 to I. Okay, if I integrate it, it becomes T by L is equal to, right, now integration of this would be log E minus IR, or let me use capital E. Okay, E minus IR, okay, and this is, you have to integrate it further, because it is you must have learned it in integration that if there is a if it's a linear term, then just differentiate it and divide it by that. So it becomes what? Minus R, minus R. Okay, further I can, okay, let me put it, okay, further if I put it in the right fashion, then it becomes L by T is equal to log E mod of E minus IR, right, minus log of E. Is that clear, guys? So what I did is I first multiplied it this side, which I did it correct. On this side it becomes log E minus IR minus log E. Why? Because here I have to use the limit I to 0. I to 0. So this becomes okay, fine. Now okay, so let me do it, okay, here. So this becomes, or let me do it here. Okay, so this becomes minus R by L, T is equal to log of E, and then E minus IR, correct, by E from here. So here, from here I have continued here. Okay, or I can say minus R by L T is equal to log of E 1 minus IR by E. Okay, further I can say 1 minus IR by E is equal to, I have removed the log, so it becomes E minus R by L and T. Okay, now I can say IR by E is equal to 1 minus E minus R by L into T. Correct? Or I can say, this is I, by the way. Oh, this is I. Yeah. Now, if I just keep I this side, so I is equal to E by R 1 minus E minus R by L T, and just close the bracket. Now see the beauty. The beauty is E by R is nothing but I naught. So let me write it here. I naught is equal to E by R. Okay, just replace it here. So this becomes I is equal to I naught 1 minus E minus R by L T. This is the final formula. Correct? It clearly states that what would be the current, and in terms of I naught, which is the maximum current, which I have written here, I naught is equal to E by R. One more thing, now what they have done is, this R by L, what they have done is, let me put it this way, उन्होंने कहा है let's tau is equal to R by L. So if, okay, I'm sorry, tau is L by R. Tau is L by R, and this has unit of time. Okay, now if I just replace it here, then I can say I is equal to I naught, 1 minus E minus T by tau, and this is the formula, just to make it more presentable. Okay. Now sometimes you get a question wherein they say define tau. Define tau. So tau is very simple way of putting it. When t is equal to tau, then I is equal to I naught 1 by e to the power minus 1, or I can say I naught 1 minus 1 by e, and the value of 1 by e is, it's a standard value, just mark it because sometimes you might need to use it, is 0.37. So I is equal to 0.63 I naught. This is I, yeah, 0.63. So just learn it. Yeah. Okay. So if we have to define tau, we will say tau is that current in which the current grows 63% of the maximum value of the current which happens in steady state. Let me reiterate it. So if we have to define tau, so you will say tau is that value in which the current grows to 63% of the maximum value. And what is maximum value? Maximum value is the steady state current. Okay. Now let's try to put a graph of whatever we have done. So we know, I is equal to I naught 1 minus E, minus T by tau. Correct? this is what we have derived in the last sheet. Now if I have to draw the graph, it would be, you know what, it is exponential. If you see, right, let's say this is the maximum current, steady state current. Okay, this is time. So if you see, the graph would be something like, not to the scale but like this. Okay, now what is tau? At what point tau comes into play? When 0.63 of I naught is there. So this is tau, and as I said, the unit of tau is time only, whatever is the unit of time, so seconds or whatever. Okay, now if I have to summarize it in terms of two small circuits, then I can say when t is equal to 0, initially I is equal to 0. Correct. Now if I put I is equal to 0 in this, so it becomes I is equal to I naught. Correct. Correct. In that case, there is no current flowing in this, and no current flows in branch containing inductor, in branch containing inductor. So at that point of time there would be no current here when t is equal to 0. Okay, very good. Let me reiterate it. So when at t is equal to 0, I is equal to 0, this current is equal to 0. Okay, so the circuit would be something like this, and in place of inductor it would be a open circuit. It would be a, I will say, open circuit. Okay, yeah. Now I will talk about second is when t is equal to infinity, which is steady state. Steady state, I is equal to I naught. Okay, why I is equal to I naught? Because if I apply t as infinity here, so it becomes e to the power, it becomes I is equal to I naught 1 minus e to the power minus infinity. Correct? And e to the power minus infinity is 1 by e to the power infinity, and 1 infinity is nothing but 0. Okay, so in that case the circuit would be inductance doesn't come into play at all. Okay, so after this let's do some questions related to it.